Have you ever just stopped and wondered, what are you really made of? I mean, if you could zoom in, right past your skin, past your cells, what would you even find? Well, you'd find the building blocks of everything, atoms. And let me tell you, the story of how we figured out what's inside these tiny atoms, it's honestly one of the greatest detective stories in all of science.
Okay, so let's dive right in. We're going to put on our detective hats and really try to solve the mystery of the atom. We'll follow all the clues, meet the main suspects, the subatomic particles, and see how each little discovery completely changed our picture of the universe.
So, here's our plan. First, we'll see how the indivisible atom was shattered. Then, we'll check out Thomson's Plum Pudding Model and what happened next, Rutherford's big surprise. After that, we'll get into Bohr's orbits, what really makes an atom's identity, and finally, the outer shell game that explains all of chemistry. It's going to be a fun ride.
So for the longest time, everyone, scientists included, thought atoms were just these tiny, solid, unbreakable little balls, like the absolute smallest thing possible. But then, as we got closer to the 1900s, some really strange clues started popping up. Clues that hinted at a whole secret world hidden inside the atom.
You know that thing you can do when you rub a comb on your dry hair and then it can pick up tiny bits of paper? Well, that's static electricity, and it turned out to be a huge clue. It meant that things could get electrically charged, and the only way that could happen is if the atoms themselves had even smaller, charged parts inside them that could be moved around. Suddenly, the uncrackable atom was, well, starting to crack.
And pretty soon, our scientific detectives found their first two suspects. First, J.J. Thomson discovered the electron, the super tiny negatively charged particle with almost no weight to it at all. And then there was a proton. It had the exact opposite charge, a positive one, but it was a total heavyweight, about 2,000 times more massive than the electron. So the big takeaway here was clear. Atoms weren't solid balls. They were made of smaller, opposite things.
Okay, so you have positive protons and negative electrons inside an atom. But how are they arranged? That was the big question. And the first person to actually propose a detailed model was the same guy who found the electron, J.J. Thomson. This was a huge deal. It was the very first time anyone tried to draw a picture of what an atom looks like on the inside. And here he is, the man himself, J.J. Thomson. I mean, think about it. He not only discovered a fundamental piece of our universe, but he also gave us the very first real idea of how to even think about it.
So, Thomson proposed what we now call the Plum Pudding Model. Just imagine a ball of positively charged pudding, and inside you have these negatively charged electrons just studded throughout, kind of like raisins. Or here's another way to think of it, a watermelon. The big red part is all the positive charge, and the little black seeds are the electrons. It was actually a really clever idea because it perfectly explained why atoms are neutral. The positive and negative charges just cancel each other out. It was a brilliant first draft.
But a good detective never just takes a theory at face value, they test it. And that's exactly what Ernest Rutherford, who was actually one of Thomson's students, decided to do. He set up an experiment to test this plum pudding idea. Honestly, he wasn't expecting anything dramatic, he probably just thought he'd confirm his teacher's work. But what he found, well, it was going to change physics forever.
So here's what they did. Rutherford's team basically shot these tiny positively charged bullets, called alpha particles, at a sheet of gold foil that was incredibly thin. Now, based on the Plum Pudding Model, where all that positive charge was just spread out like a fine mist, you'd expect these alpha particles to just zip right through, right? Maybe they get nudged a little, but they should basically go straight. That was the whole idea.
But that's not what happened. I mean, yes, most of the particles did go straight through, just like they thought. But about 1 in every 12,000 particles did something that should have been totally impossible. They bounced back. Some got deflected at these huge angles, and a few of them literally came flying right back at them.
And you can just feel the shock in Rutherford's own words. He said it was as incredible as if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you. Can you imagine? This one result just completely demolished the Plum Pudding Model. There was no way to explain it unless the positive charge in the atom wasn't spread out at all.
This stunning result led Rutherford to a completely new, radical model. He realized two things. First, most of the atom must be just empty space. That's why most of the particles flew right through. But second, all the positive charge and almost all the mass had to be crammed into a super tiny, super dense center, which he called the nucleus, and the electrons? They must be orbiting this nucleus, kind of like planets orbiting the sun.
Now, Rutherford's nuclear model was a massive step forward, but it had one huge fatal flaw. See, according to the laws of physics at the time, an orbiting electron should be constantly losing energy, and if it loses energy, it should spiral inwards and crash right into the nucleus in like a split second. So his model basically predicted that all atoms should just collapse. But obviously, they don't. We needed another brilliant mind to solve this puzzle.
So on one hand, you have this big problem, the death spiral of the electron. And on the other, you have the amazing solution from physicist Niels Bohr. He proposed something that was completely out there. He said, what if electrons can't just orbit wherever they feel like? What if they're stuck in very specific, allowed orbits, or energy levels? And the kicker is, while they're in one of these special orbits, they just don't radiate energy. It was a bizarre new rule for how the universe works, but it did the trick. The atom was finally stable.
Okay, so we have a stable model. There's a nucleus in the middle and electrons orbiting it. But what's actually inside that nucleus? And more importantly, what makes an atom of carbon, say, different from an atom of gold? To answer that, we have to look right into the heart of the atom. Well, for a little while, there was one last mystery. Scientists noticed that the nucleus was always heavier than it should be if it only had protons. There was some missing mass. The final piece of this puzzle was found in 1932 by James Chadwick. He discovered the neutron. And just like the name sounds, it's neutral. It has no charge, but it weighs almost exactly the same as a proton, and it lives in the nucleus, making up all that missing mass.
So now that we have all three particles, we can finally define what makes an element, well, an element. It's all about two numbers. First is the atomic number. This is super simple. It's just the number of protons. And this is the atom's ultimate ID card. It's what defines it. A carbon atom always has 6 protons. Always. Then you have the mass number, which is just the protons plus the neutrons. That basically tells you how heavy the atom is.
And this is where things get interesting, because you can have different variations. For example, you have isotopes. These are atoms of the very same element that have a different number of neutrons. So for instance, all carbon atoms have 6 protons, but carbon-12 has 6 neutrons, while the famous carbon-14 has 8 neutrons. Then you have isobars. These are atoms of different elements that just happen to have the same total mass, like argon and calcium. Totally different elements, but both can have a mass number of 40.
All right, so we've cracked the nucleus. Now let's shift our focus to the outside of the atom, to the electrons. Because how these electrons are arranged, well, that's the key to basically all of chemistry. Seriously, it's what decides how atoms bond, how they react, and how they build up the entire world we see around us.
So, how do the electrons fill up those energy shells we talked about? Turns out there are some very specific rules to this game. Rule number 1, each shell can only hold a specific number of electrons. Rule number 2, and this is a big one, the outermost shell, the one on the very edge, can hold a maximum of 8 electrons. And rule 3, you have to fill the inner shells first before you can move to the outer ones. Inside out. Simple.
This all leads to a really important idea called valency. So if you think of an atom like a person, what does it want more than anything? It wants a full outer shell of electrons. That's when it's happy and stable. And valency is just a measure of its power to make that happen. It tells you how many electrons it needs to gain, lose, or share to get that perfect, stable set of 8 electrons, which we call an octet. This one desire is what drives pretty much every chemical reaction.
Let's make this real with a few examples. Look at hydrogen. It has just 1 electron, so it's super eager to give it away. Its valency is 1. But then you have helium and neon. Their outer shells are already full, so their valency is 0. They're totally content, stable, and don't want to react with anything. That's why we call them the noble gases. Now what about carbon? It's got 4 electrons in its outer shell. It could gain 4 or lose 4, which makes it incredibly flexible. That's why it's the basis for all life. And oxygen. It has 6. It's so close to a full shell of 8, so it desperately wants to grab 2 more electrons from somewhere. Its valency is 2. So there you have it. We went from thinking the atom was a solid, unbreakable ball to understanding it as this complex, beautiful dance of electrons in special shells around a tiny, dense nucleus. It's been an amazing journey, right? Each model we talked about was a crucial step, all built on clever detective work. It really makes you wonder, doesn't it? Our model today is amazing, but science is never finished. What other secrets are still hiding inside the atom? And what incredible questions will the next generation of scientists even think to ask?